right, so today we're going to talk about the first law of thermodynamics. The objectives for this lesson. At the end of this lesson, you should be able to describe the relevance of energy to physical and chemical changes, describe equilibrium, state functions, and path functions, describe and differentiate heat from work, relate heat flow to temperature changes and phase changes, determine work associated with volume changes, describe the first law of thermodynamics, and interpret heat and work from a molecular perspective. Okay, so let's start off with chemical thermodynamics. What's thermodynamics? It's a study of principles pertaining to both properties of matter involving energy. So it's, what makes it, when you apply it to chemistry, okay, you have chemical thermodynamics. So we're basically interested here in the energy changes that accompany chemical changes, actually physical and chemical changes. So the question is, why do we study chemical thermodynamics? One of the most basic questions that we can answer with chemical thermodynamics is how far will a process go before it reaches equilibrium? What do we mean by equilibrium? When something has reached equilibrium, that means it stops. Okay, so in other words, how far will a process go before it actually stops? So what's the link between that and measurements of heat? That would be our main concern. Okay, so we're going to start off by talking about energy and heat, and then eventually, sometime later this semester, we'll be able to make the connection between heat and equilibrium. So some terminologies we need to be familiar with. Whenever we use the word system, okay, we're referring to any part of the universe that we're interested in, okay? And so, for example, typically what would be the system we would be interested in chemistry would be a reaction mixture. Everything else in the universe would be called the surroundings, okay? And generally we're just interested in the immediate surroundings of whatever system we're interested in. The wall is a boundary between the system and the surroundings, okay? Now, the concept of equilibrium. A system, we say, is in a state of equilibrium if it's not changing. All of its properties are well defined. Okay, so there's no changes that you're seeing in your system. And so equilibrium basically is what we're saying is the ultimate fate of all processes. Eventually everything stops, reaches equilibrium. So how do we define actual equilibrium from an operational perspective? You can say that a system is at equilibrium if it's at thermal equilibrium. There's actually three conditions it has to satisfy. It has to be at thermal equilibrium, it has to be in mechanical equilibrium, and it has to be in material equilibrium. So there's three conditions that must be satisfied for us to be able to say that the system is at equilibrium. So what does thermal equilibrium mean? We say that a system is in thermal equilibrium if its uniform is constant and uniform throughout and it's not changing. Okay? So if you're allowing energy to flow between your system and your surroundings, then your system must be in, we say it's in thermal equilibrium with your surroundings if they are at the same temperature. Okay? So if your system and surroundings are at the same temperature. Now, if your system is separated from the surroundings by adiabatic walls, the word adiabatic walls means it's thermally insulated. So if you're not letting heat flow between your system and your surroundings, then you say your system is at thermal equilibrium if the system itself has a constant temperature, okay, and that temperature is uniform throughout the system. Mechanical equilibrium. When is mechanical equilibrium established? If the volume of your system is not changing, okay, so that means the walls are not moving, it's not expanding, it's not contracting, its volume is fixed, then we say it's at mechanical equilibrium. What that means is, so if you have a system right here, okay, at the boundary between the system and the surroundings, the force per unit area that the wall is experiencing from the system side would be equal to the force per unit area that the wall is experiencing from the other side. So it's getting equal push from both sides, so it's mechanical equilibrium. It's not going to move, right? So we define P, the force per unit area, as the pressure of the system, and then the force per unit area from the outside would be your external pressure. So what happens when those two are not equal? Then we say we're not at mechanical equilibrium. Your wall is going to move, so you either squeeze your system, okay, or your system will expand, okay. So when will it, in what case will your system be squeezed? When the pressure outside is higher, okay. And when will it expand? If the pressure inside is higher than the outside pressure. Material equilibrium happens when your system's composition is fixed. That means there's no more chemical reactions going on. All chemical reactions have stopped. Every substance that's present in your system will have a fixed constant amount if it's at equilibrium, at material equilibrium. So no net chemical change, and there's no net phase change. You're not seeing any solid turning into a gas or gas turning into solid. So it looks like everything has stopped. It looks like there's no changes there in the composition of your system. So, in that case, you'll reach material equilibrium. Of course, we know at the atomic level, okay, processes actually continue to happen because atoms and molecules are constantly moving. So even if we see a reaction appearing to have stopped at the atomic level, it hasn't really stopped. It's just that reactions are reversible. So if you have reactants colliding to make products, products will collide back to make reactants. And chemical equilibrium we say is established when the rate at which the forward reaction is equal to the rate of the reverse reaction. But thermodynamics is really concerned more at the macroscopic level. That means what we can see from the outside, not at the molecular level in terms of the concept of material equilibrium. Okay? So material equilibrium actually is what we might call a dynamic equilibrium, because at the atomic level, nothing has really stopped. It just appears as though it stopped because you got two opposing processes, one going forward, the other going in reverse, happening at the same rate. Okay, so the state of a system then that is at equilibrium can be specified by specifying three things: the temperature, the pressure, okay, and the phases present and the amount of each type of molecule or ion that's present in each phase. Because it's at thermal equilibrium, so its temperature is well defined. It's at mechanical equilibrium, so its pressure is well defined. And it's at material equilibrium, so its composition is well defined. If you specify all of those, you're specifying what's called the state of your system, or the equilibrium state of your system. Okay? That's how you specify an equilibrium state. Now, we can make a system undergo a change from one equilibrium state to another by manipulating the surroundings or the boundary between the system and the surroundings. Basically, we can make change happen by disrupting thermal equilibrium, mechanical equilibrium, or material equilibrium. For example, let's say you have a pot of water at room temperature. It's not doing anything. You're looking at it, it's fixed temperature, it's not changing its volume, so we say it's at thermal equilibrium, right? So mechanical equilibrium. How do we make that pot of water change? Well, you put it on a hot stove, you change the surroundings, so the surroundings is now hotter than the system. What will happen if you place something hot in contact with something cold? What happens to the pot of water if you put it in a hot stove? Temperature increases, right? So there's going to be a change in the water. By changing the surroundings of your water, you've caused a change to occur in the water. The temperature goes up. What about you have an inflated balloon? What happens if you squeeze it? What are you doing? You're increasing the external pressure. And so by doing that, the wall between your system and the surrounding moves. Okay? What if you pour acid on a metal? Generally, your metal will react with the acid, a chemical reaction will occur. You're changing the environment of the metal. The metal might just be sitting on a bench top, not doing nothing, but if you change its surroundings, you put it in a beaker full of acid, a chemical reaction can occur, so you're altering you're causing a change in the state of your system. Right. State functions, The word state function refers to a property of a system. So it's a well-defined value for a given equilibrium state. So examples of state functions would be temperature. Okay. If it's systems at equilibrium, its temperature is well-defined. So temperature is an example of a state function. Pressure, volume. Okay. Things you can use to describe a system at equilibrium are called state functions. Okay? They do not depend on the history of the system. In other words, it doesn't matter how you got to that point. It doesn't matter how the system got to that particular state. These state functions are well defined. So if a system ever undergoes a series of changes and it goes back to that particular state, those values would still be the same. Otherwise, it would be a different state. So state functions, we say, are not path dependent, okay? It doesn't depend on how you got there. They're path independent. Path functions, okay, are quantities that depend on how you got to your final state, your current equilibrium state. So this would be the opposite of a state function. So examples of path functions are work and heat, okay? Path functions depend on how you get there. So if you reach a particular state and it requires heat or work to get there, it depends on what you actually did to get to that particular state. So work and heat are examples of path functions. Heat and work. Let's define heat and work. Heat, okay, is the energy that flows between two systems because of a temperature difference. So heat is something that goes from one system to another because they happen to be at different temperature. Okay, and that thing that flows, we now know we've now identified that as energy. Okay, so when the system and the surroundings are not in thermal equilibrium, you say you're going to have heat flow. Okay. Now, any other way of transferring energy is called work. So any other way of transferring energy that cannot be classified as heat would be a transfer of energy by way of what we would call work. Okay? So if a system's temperature changes, okay, it doesn't necessarily mean heat is flowing into or out of your system, because a temperature change could occur if there's an energy flow into the system. It doesn't have to be done by heat. You can do it by work. So think of heat and work as just two ways of transferring energy. Okay? When is a particular transfer of energy considered a heat flow? That is if that occurred because you put something hot in contact with something cold. Any other way that you transfer energy would be what you would call work. Okay? All right. So, in which of the following is the observed temperature change due to heat? Given the definition of heat and work, is it A, rubbing two hands together? What do you notice when you rub your two hands together? It gets hot, right? Are you heating your hands? If you hit a hammer with a nail, you'll notice if you touch the nail, it gets hot, right? Did you heat it? Is that temperature change due to heat? Or if you put a pot of water on a hot stove, is that temperature change because of energy transfer by way of heat? So which of these is due to heat? Correct answer is C. Okay? So rubbing two hands together, okay, unless one hand is hotter than the other one to begin with, the increase in temperature there is not due to heat. Okay? That would be mechanical work. Hitting a hammer with a nail, that's also, you're not heating it. You're causing its temperature to rise by giving it energy, and the energy was transferred to it in the form of work. Okay? Heat is energy that's transferred because you put something hot in contact with something cold. Okay? So, here's another example. If you pass electricity through a wire, so let's say you have a piece of wire, you dip it in water. Okay, you pass electricity through your wire, and the temperature change. Temperature of the wire will increase, and the temperature of the water will increase. So the temperature increase in the wire, is that due to heat or work? And the temperature of the water, the change in the temperature of the water, is that due to heat or work? What would go into these blanks right here? So correct answer. In both cases, when you're pushing your electrons through your wire, causing your wire to increase, you're not putting your wire in contact with something hot. Okay, so that's work. That's called electrical work. So the wire got hot because of electrical work. Now, since the wire got hot, you're now putting the hot wire in contact with the cold water. So the increase in the temperature of the water is now, we say, is due to heat transfer from the wire to the water. Okay? So the correct answer there is B. All right, some sign conventions when we're dealing with heat and work. Okay, in the case of heat, the letter Q is a commonly used symbol for heat transfer. And we say that if heat goes into a system, okay, then we say that the energy of the system increases. So we assign a positive value for heat. Okay, so we say when a system absorbs heat, we're looking at a process that is endothermic. Endo means going into, right? Thermic has to do with heat. So when Q is Q is assigned a positive value when heat flows into your system. If heat flows out of your system, we assign a negative value for Q, because that would mean what? If heat flows out of your system, the energy of your system is dropping. Okay? So we assign a negative value for Q. So let's just quickly check that concept. A pot of water at room temperature is placed on a hot stove. Let's say 5,000 calories of heat is transferred. Q for the pot of water is blank, and Q for the stove, and Q for the stove is blank. Ready? Water is colder than the stove, so the energy transfer is from the stove to the pot of water, right? Need one more. So, okay, for the pot of water, did heat energy go into the pot of water? It got in temperature increase. So energy flows into the water, so positive Q for the water and negative Q for the stove. Good. Really simple ideas. How do we measure heat? Okay, assuming there is no chemical or physical change, there's no phase change, and there's no phase change. That means there's no changing from solid to liquid or liquid to gas. Those are phase changes. So assuming no phase changes and there's no chemical reaction happening, heat flow will cause a temperature change in your system. The amount of heat, we say, is we're going to use the measured change in temperature as a way of measuring the amount of heat. We say that the amount of heat is directly proportional to the change in the temperature. In other words, if you observe a bigger change in temperature, means you put in more heat, right? So a bigger delta T would give you a larger Q. Delta T, the change in temperature, is final minus initial. And note that this is a change in temperature, so delta T, the unit for delta T can be degrees Celsius or Kelvin, and it will have the same value whether you express it in Celsius or Kelvin. Why is that? let's say you went from 20, let's say from 0 degrees Celsius to 5 degrees Celsius. What's delta T for that one? That's 5 minus 0. 5 degrees, right? But what would that be in Kelvin? What's 0 degrees in Kelvin? 273, right? And what's 5 degrees in Kelvin? 5 plus 273 is 278. So what's delta T in Kelvin? It's also 5 Kelvin, okay? So keep that in mind. Anytime you're looking at temperature changes, whatever the temperature changes in Celsius, that's the same temperature change in Kelvin. Okay. So, delta T is final temperature minus initial temperature. This proportionality constant here, the C, is called the heat capacity of your system. That you can define that as the heat needed to increase the temperature of your system by 1 degree. Here's a way of looking at it. If we rearrange this equation right here, okay, we can solve for C. C is Q divided by delta T. So the unit for that is what? An energy unit, which is joules per Kelvin, temperature unit. Okay, that would be our unit. Or you can say it's joules per degree Celsius. So that's your heat capacity. So that's the amount of energy in joules needed to cause a temperature change of 1 degree Celsius or 1 Kelvin. Right? Unit for Q is calories or joules, and 1 calorie is 4.184 joules. Okay? Maybe if you're wondering why that odd conversion factor, that's because the calorie was defined first as the energy needed to change the temperature of 1 gram of water by 1 degree Celsius. Okay? And it was only later that James Joule was able to establish that heat is just another way of transferring energy. It's equivalent, and they've already defined energy units. And so the equivalent unit for the equivalent amount of energy for 1 calorie was found to be 4.184 joules. Okay. So let's look at some simple examples. Let's say it takes 8.4 times 10 to the third joules of heat to raise the temperature of a sample of water from 25 to 35 degrees Celsius. What's the heat capacity of the water? What's our formula for heat capacity? Capacity is Q over delta T. I'll give you a couple of minutes, not a couple of minutes, should take you only like 20 seconds to figure it out, right? So anytime you're ready, click your answer. Okay, let's see. Q is how much? 8.4 times 10 to the third joules. And the temperature change, T final minus T initial, that's 10.0 degrees Celsius. So 8.4 times 10 to the third divided by 10 would be 8.4 times 10 to the 2 sig figs, joule per degree Celsius. So it's A. Joule per degree Celsius is the same thing as joules per Kelvin or joules Kelvin to the -1. Okay? Same unit. Okay, heat capacity of a metal is 25 joules per Kelvin. Calculate Q if its temperature drops from 20 to 16 degrees. Assume no chemical or phase change. What is Q? What's the formula for Q? Q equals C delta T. Anytime you're ready, click your answer. erase it. Okay, D is a popular answer. Let's see if D is the correct answer. Q equals heat capacity is 25.0 joules per Kelvin. And delta T is 16.0 degrees Celsius minus 20.0 degrees Celsius. Okay, so that's 25.0 joules per Kelvin. 16 minus 20 is negative 4.0 degrees Celsius. Okay, a change of 1 degree Celsius is equivalent to a change of 1 Kelvin. So we do that just for unit consistency, so that you can cancel Kelvin over here. So negative 4 times 20 would be negative 100, 2 sig figs, okay, joules. So negative 1.0 times 10 to the 2 joules. Answer is D. Okay, so D is the correct answer. Okay. Specific heat and molar heat capacity. Specific heat, anytime you put the word specific in front of a quantity, that you typically means per gram. So specific heat capacity means heat capacity per gram. Okay, and oftentimes that's just shortened to just specific heat. So when we say specific heat, what we really mean is heat capacity per gram. Now, so if you know the specific heat, okay, all you have to do is multiply that by the actual mass in grams to get the heat capacity. So specific heat times the mass would give you the heat capacity, right? So what's the specific heats are available only for homogeneous samples. Why is that? What do we mean by homogeneous? It's uniform throughout, right? If you have a sample that's not uniform throughout, then different parts of your system might have different heat capacities. So they're going to have different specific heats. So specific heats are things you can look up, for example, for pure substances. So if you have a sample of a pure substance, you would know what its specific heat is. Okay. So what molar heat capacity, on the other hand, is just like specific heat. It's this one is heat capacity per mole. So if you can look up the heat capacity per mole, the molar heat capacity, all you have to do is multiply that by the number of moles. For most substances, that's how heat capacities are actually tabulated on a per mole basis. Okay, there's a few things where you have tabulations of specific heats. If you look up heat capacities from tables, handbooks, or online, most of the stuff you'll find for substances are given in molar heat capacity. It's per mole. Okay, and they're only defined for pure substances. Okay, so given that information, let's say you have the heat capacity of 200 grams of iron is found to be 90 joules per Kelvin. What's our specific heat and what's the molar heat capacity? Okay, heat capacity is what? Mass times specific heat, right? Or moles times the molar heat capacity. So how do we get specific heat? It's just heat capacity divided by the mass, right? So what's our heat capacity? 90.0 okay, joules per Kelvin. And what's our mass? 200.0 grams. So what's 90 divided by 200? 0.45 exactly. So 3 sig figs, 0.450 joules per Kelvin per gram. So the unit for specific heat is a unit for heat capacity per gram. Okay, so you can write it as joule per Kelvin per gram, or you can say joules, per Kelvin gram. Okay, or you can say joules per degree Celsius per gram. Okay, those are all units for specific heat. What about molar heat capacity? What's the molar heat capacity for our sample? C sub m is capacity over number of moles. So what's our C? 90.0 joules per Kelvin. How many moles do we have? You have to change 200 grams to moles. What information do you need to change grams to moles? Molar mass. 200 grams of iron. What's the molar mass of iron? How much? 55.85 grams per mole. Okay. So grams cancel out. Okay. So the molar heat capacity for iron is, what would that be? 90 divided by 200 times 55.85. That's 25.1. Okay. 25.1 joules per Kelvin per mole. So you can write it as joules per Kelvin per mole. Okay, that's your molar heat capacity. There hasn't been a consistent symbol that people use for a specific heat. Some textbooks use C sub S, some textbooks use SPHT, some textbooks use lowercase c, some textbooks use lowercase s, so just be aware of that, okay? If you want to know if your particular heat capacity is given to you as a specific heat, just look at the units. If it's joules per unit change in temperature per gram, then you know you're referring to the specific heat. Okay? So, just be aware of those. Okay. Specific heat of water is 4.18 joules per Kelvin per gram. What's the molar heat capacity of water? How would you do this? You just say 4.18 joules per Kelvin per gram, right? I'm just going to put per gram here so I can quickly change this. How do I change it to per mole? One mole of water is how many grams? 18.02 grams. Okay, so what's 4.18 times 18.02? .3 joules per Kelvin per mole. Okay. All right. The molar heat capacity of a solid metallic element is approximately equal to 3R at room temperature, R being the gas constant, 8.314 joules per Kelvin per mole. Okay. This is known as the law of Dulong and Petit. And it's a good way to determine the specific heat. A lot of times we're interested in the specific heat, okay? But this is a very good number to remember. But this is per mole, so you can just change it to per gram if you want the specific heat. So what is 3R? 3 times 8.314 joules per Kelvin per mole. If I want to make that per gram, what should I do? For iron, what's the molar mass of iron? 55.85 grams for 1 mole. Okay, so moles cancel out. This will give you how much? 0. We had that earlier, right? Three times, times 1 divided by 55.85, 0.45. Okay, let's see. 3 times 8.314 divided by 55.85, 0.4, 0.46, 0.45. Okay, I'm just doing two sig figs here. Joules per Kelvin per gram. Okay. All right. Here's a clicker question. Specific heat of water is 4.18 joules per Kelvin per gram. Specific heat of iron is 0.45 joules per Kelvin per gram. Which sample releases more heat if cooled from 100 degrees to 37 degrees? In other words, if you're given a choice, hold a piece of iron that's at 100 degrees or dip your hand in water that's at 100 degrees, which torture would you choose? Which is the less evil torture, the less desirable? Which torture is less undesirable? Huh? Mm, if you're, assume you're not allowed to pick none of the above. Which one would release more heat? Oh, okay. What's the formula for Q? C delta T, right? And what is C? It's mass times the specific heat. I'm going to use C sub S. I like this new notation that I've been seeing in recent textbooks. C sub S for specific heat. Okay. Heat capacity is mass times specific heat. You're looking at the same delta T, right? From 100 degrees to 37 degrees. You're looking at the same mass. So which one will give you a bigger Q? Let's try again. See, if it has to cool down from 100 to 37, it has to release heat, right? In fact, Q here is going to be negative. Okay, water. Okay. Water releases more heat. Very good. How do you determine specific heat? What you can do is you can mix something hot and something cold in an insulated container called a calorimeter. So here's a picture of a calorimeter. Okay, this is an experiment where you put water inside. So you have water inside. And in here you have your sample, like maybe a piece of metal. So here's your sample, okay, at a different temperature. Okay, you mix the two. Okay, so in a calorimeter, you have an insulated apparatus for measuring heat measurements. So because the calorimeter is insulated, Q must be equal to 0 inside the calorimeter. So Q for everything going on inside your calorimeter plus, okay, you have C cal delta T cal must be 0. What is this C cal times delta T cal? This C cal right here is the calorimeter constant. That's actually, okay, you mix two things, but then you're not really just having those two things in there, because in addition to the two things that you're mixing, you got the immediate surroundings, which would be the air above your sample, okay, the walls of the calorimeter, and there's a thermometer that you have in there, there's a stirrer that you use to mix the two things that you're putting together. So all of those extra stuff in there will absorb some of the heat or will release some of the heat depending on what's going on. So we lump all the heat capacity of all of these things into just one value. So you call that the calorimeter constant. Okay. So your delta T cal would be the change in the temperature of all of these other things. So how do we do this? Okay, let's illustrate that with a problem. You have a 70-gram sample of metal, okay, with a specific heat of 0.3 joules per Kelvin per gram at 100 degrees. So you have a hot piece of metal, 100 degrees, okay? You pour it into a calorimeter that has 100 grams of water at room temperature of 20 degrees. What happens? The water gets warmer. It becomes final temperature of the whole thing becomes 23 degrees Celsius. So the metal, which used to be 100 degrees, is now at 23 degrees. The water, which used to be at 20 degrees, is now at 23 degrees. So you know the specific heat of water, you know the specific heat of the metal, you can figure out the calorimeter constant. The way you do this is you say Q of the metal, okay, plus Q of the water, plus Q of the calorimeter must be equal to 0. Okay? What's Q of the metal? Mass of the metal times specific heat of the metal times delta T for the metal. It's Q of the water. Mass of the water, specific heat of the water times delta T of the water. And what's Q cal? The calorimeter constant times delta T for the calorimeter. What's delta T for the calorimeter? That's the same as the delta T for the water, because initially you have your water in your calorimeter. So this delta T for the water is the same as the delta T for the calorimeter. And you know all your delta T's, you know all your masses, you know your specific heats. What's the only unknown here? This one is your unknown, okay? And so this whole thing is equal to 0. How do you solve for your unknown? You move all of this to one side and then divide by that, right? So you say C cal, the calorimeter constant, would be equal to negative of Q metal minus Q water. Okay, this is Q metal, that's Q water. You move it to the other side, divided by delta T cal. Right, so what's our Q metal? Mass of the metal is how much? C of the metal is how much? Delta T for the metal is how much? Q of the metal. Okay. Mass of the metal is 70 grams. Okay. 70.0 grams. What's the specific heat of the metal? 0.300 joules per Kelvin per gram. Okay, let me put those units in. Joules per Kelvin per gram. So gram cancels out. And what's the delta T for the metal? Negative 77. It went from 100 to 23, right? So 23 is the final minus the initial, which is 100. So this would be negative 77.00. Negative 77.0 Kelvin. So Kelvin cancels out. So that's Q for the metal. And don't forget, we need to put a negative here, right? Okay. So that's negative of Q metal. And then minus Q of the water. What's Q of the water? Mass of the water is how much? 100 grams. Specific heat of the water, you should know, is 4.18, okay, joules per Kelvin per gram. So gram cancels out. And delta T for the water. How much did the water change? From 20 to 23 degrees Celsius. So that's 3.0, right? So 3.0 Kelvin, that cancels out. And then you divide the whole thing by delta T cal, which is what? What's delta T cal? The same as delta T for the water, so divided by 3.0 Kelvin. Okay, let's look at some numbers here. What are these numbers? So that's negative of Q metal. What's our Q metal? 1,000, negative 1,617 joules. Why negative? The metal was hot, it got cold. So heat flow, we say there was a heat flow out of the metal. Okay? Minus Q of water is how much? 1,254 joules. Positive, right? Why positive? The water absorbed heat. So 1,600 went out of the metal, okay? But only 1,200 went to the water. Where did the rest of it go? The rest of the calorimeter, the stirrer, the thermometer, the air above it, in immediate surroundings, okay? So that's the amount of heat that did not transfer from the metal to the water. So this difference right here. And so you divide this one by delta T, which is 3.0 Kelvin. What do you get now? Okay, let's look at our sig figs. This should have 3 sig figs, right? And this one should only have 2 sig figs. But we'll keep those extra numbers just for safety. You don't want to build up round of errors. So what do you get? 1617. Negative, negative, that's plus, right? 1617 minus 1254. That difference of 363, okay, joules is the amount of energy that did not transfer from the metal to the water. It went to the rest of the calorimeter. Divided by 3.0 Kelvin, okay. So what would this be? 363 divided by 3. 121 joules per Kelvin. Okay. Now, how many sig figs should we have here? If we go by the sig fig rules, okay, this the last sig fig there is in the hundreds, the last sig fig there is in the tens, so we really should have just sig figs in the hundreds. So there's really only one sig fig here. Okay, so only one sig fig left. So it's about 100 joules per Kelvin. But usually when you determine the calorimeter constant, you're going to be using it for further calculations. Okay, the calorimeter constant is just a way for you to calibrate your calorimeter. So now, once you've calibrated it, you can use it to determine the heat capacity of an unknown substance. So what we're doing here when we're determining the calorimeter constant is we're calibrating our calorimeter. We're checking it out using known quantities. So 2 known substances with known heat capacities, known amounts. Okay, so we can figure out how well that calorimeter handles the heat transfer. Okay, so although you should only have one sig fig here, usually we keep extra digits there because we're going to be carrying over that number to another calculation. All right. So here's an example of a follow-up to that. In this case, now you have a calorimeter that you have calibrated, so you know your calorimeter constant is 125 joules per Kelvin. Okay. So this time you mix a 150 gram sample of a metal, unknown sample. Now you don't know your heat capacity. You're being asked for the specific heat of the metal. Okay, so this is now your unknown run. And then you pour it in a calorimeter containing 100 grams of water at 20 degrees. So your metal again is hot, your water is hot. You know how much heat your water is going to absorb. You can calculate it, right? But as far as your metal is concerned, the specific heat is unknown. So what should we do? We say Q metal plus Q water plus Q cal is equal to 0, right? It's a basic equation in calorimetry. All the Q's add up to 0 because in calorimetry, your calorimeter is insulated. So what is C cal? It's Q cal is C cal times delta T cal. What's Q water? Mass of water times specific heat of water times delta T of your water. What's your Q metal? Mass of the metal times specific heat of the metal times delta T of your metal. Okay? All of that should add up to 0. What's my unknown here? I know my delta T cal. What's my delta T cal? It went from 20 degrees to 24.5. So this is 4.5 degrees Celsius, right? C cal, I know, is how much? 125 joules per degree Celsius or joules per Kelvin. So I know that. Delta T for the water is 4.5. It started out at, okay, let's call that Kelvin instead of Celsius for consistency. It went from 20 degrees Celsius to 24.5. Specific heat of water, do we know? 4.18 joules per gram per Kelvin. Do we know the mass of the water? The mass of the water was 100 grams, right? Do you know delta T for the metal? The metal started off at 100 degrees and it ended up at 24.5. So what's delta T for the metal? Negative 75.5. Keep that in mind, that's negative, okay? Do you know the mass of the metal? 150 grams, right? So what's the only unknown here? Specific heat of the metal. So you have all the information you need to solve for the specific heat of the metal. So I'm not going to go into the details of that calculation. You should be able to work it out, okay? All right. So let's summarize the procedure for determining specific heat. You do a standard run, right? You mix two known things. Usually one of them would be water, and then the other one would be some other known metal, okay? You look up the specific heat of the known material. So calculate Q water, Q known, and Q is mass times specific heat times delta T. Then you can calculate Q cal, given that all of those Q's should add up to 0. And then from that, you can calculate the calorimeter constant is just equal, given that Q cal is C cal over delta T. So that was the first example we had. And then the follow-up question was one where we had an unknown run. Okay. Now, sometimes, oftentimes, in fact, in textbooks, they give you problems for determining specific heat. And in those cases, oftentimes you are asked, you have to make the assumption that Q cal is 0. So if you don't have information about the calorimeter constant, if you're given a problem, just assume it's 0. Okay. That's just to make things simple. But in practice, you really need to do a calibration of your calorimeter, and that means you have to do a standard calibration. Okay. Now, phase changes. That's changing from solid to liquid, liquid to gas, and so on. Heat flow does not necessarily involve a temperature change. Okay. In fact, let me show you this website right here where you have a substance, a pure substance being heated. So let me do a search for that website. Let's see. Search for, might as well just type it in. Let's see. Davidson.edu, heating curve. I'll just do a search. Do a search for heating curve, davidson.edu. Okay, and there's our website right there. Here's an illustration of what happens when you have a pure sample, a pure substance, and you were to heat it. Can't seem to get it to run. Oops, there it is. So imagine this is a sample right here of a pure substance, this blue thing right here, okay? And I'm going to heat it, so I'm going to click on this heat button and see what happens. You're plotting here temperature versus the heating time, okay? So I'm going to keep heating it. What's happening as I'm heating it? The temperature went up, right? But after a while, I keep heating it, the temperature doesn't change. Why is that? Look at what's happening here. Okay, this is here you have, this is what happens when your solid starts to melt. While your solid is melting, if you have a pure substance, while it's melting, the temperature will not be changing even if you continue heating it. Okay? Eventually, once everything's melted, so here, once your all of that blue disappears, so all of your solid has turned to a liquid, then heating will now lead to increase in the temperature. But then if you continue heating, eventually what happens? It will start boiling. Okay, your liquid will start to change into a gas, and when that's happening, again, your temperature will remain constant while your liquid is still boiling until everything has been converted into a gas. Okay, you can see going from a liquid to a gas is a very big change in the volume, a huge expansion in the volume. Okay, and then once everything is vaporized, then further heating will allow your gas temperature to increase. So this is what's called a heating curve. So this, oops, what happened? So this is what you would call your melting point or freezing point. Why is the melting point and freezing point the same? The temperature where a solid melts is the same temperature where the liquid freezes. So freezing point of water is 0 degrees Celsius. That's the melting point of ice. And over here, that's your boiling point. Okay? So while something is boiling, then the temperature doesn't change. So the amount of heat, okay, that was needed to boil off your water from here to here. So this difference right here, that's called the heat of vaporization. The Q for this, okay? Now this one, it's not this difference on the graph, because on the graph what you have here is time, okay? So the amount of heat that's needed to go from this point in time to that point in time, that is the heat of vaporization, or delta H of vaporization. Delta H with a V in between the delta and the H, okay? And what do you call the amount of heat needed to melt your, from this point on, from this point to this point right here on your diagram, the amount of heat you need for that to happen is called the heat of fusion. So the amount of heat you need to melt something is called the heat of fusion. The amount of heat you need to vaporize something is called heat of vaporization. Okay? So, to go from solid to a liquid, the amount of heat you need is called the heat of fusion, delta H with an FUS in between the delta and the H, or you can put the FUS after the H. The amount of heat you need to change a solid to a gas, if a solid happens to just change to a gas directly without melting, without turning into a liquid, that process is called the heat of sublimation. And to change the liquid to a gas, the amount of heat you need for that is called the heat of vaporization. These are all endothermic processes. They require heat, okay? So Q for these are positive. Now, if you go look at the reverse process, if you want a liquid to change into a solid, okay, then what would you have to do to turn a liquid into a solid? You have to take energy out of your liquid, okay? So it has to be an exothermic process. So if you want a gas where your molecules are moving more or less freely, if you want to restrict the movement of your molecules so they can condense into a liquid, what do you have to do? You have to take energy out from those molecules so they So when you condense a gas or liquid, energy has to be taken out of the gas. So Q for those are negative. Those are exothermic processes. And the amount of heat required is just the opposite of the opposite process. So delta H for freezing will be just the negative of the delta H for melting. Okay, so if you want to know the delta H for the freezing of something, you look up the delta H for melting and then take the negative of that. Okay, same thing for gas to solid, the delta H for the deposition of the gas to a solid will just be the negative of the delta H of sublimation. Okay. Let's see. Some clicker questions here. Person with a fever, 38 degrees, is given an alcohol rub. Okay, as the alcohol evaporates, what's Q for the alcohol? And what's the Q for the person's skin as the alcohol evaporates? Is it positive for both? Positive for one, negative for the other, negative for one, positive for the other? Or is it both negative? So what do we know about vaporization? Endothermic. So Q is positive. Okay? And so the energy goes to the alcohol molecules as they leave the skin. So what happens to the skin? You have a negative Q for that. Well, what happens? You feel cold, right? So you lower the temperature of the body. It's a quick way to quickly lower the temperature of a person with a fever. And that's the same reason why if you come in from the rain, you're drenched, or you come out of a shower, and as the water evaporates from you, what happens? You feel cold, right? Because the energy is being drawn away from your body by the molecules of the liquid turning into a gas. Okay, which of these is endothermic, A, B, or C? Ready? I forgot to record again now. Did I forget to record? Okay. All right. Liquid to gas, that's vaporization, so that's endothermic. Okay. Liquid to solid, that's freezing, right? So that's exothermic. Q is negative. Gas to liquid, that's condensation. That's also exothermic. Correct answer is that. Let me see. I am recording. Good. I don't have to re-record like I did the other day. Okay. Why is steam more dangerous than boiling water? Calculate Q for converting 1 mole of steam to liquid water. Usually these delta H values for fusion, vaporization, they're given either on a per gram basis. So if you look them up, you'll find the values on a per gram basis or per mole basis. Okay, so if you need the actual amount of heat involved, you have to multiply those values by either the amount in grams or the amount in moles. Okay, so delta H for vaporization of water is, if you look it up, you'll find it to be 40.7 kilojoules per mole. Okay, and of course you know specific heat of water is 4.18 joules per gram per degree. Okay, so why is boiling water more dangerous than, why is steam more dangerous than boiling water? Well, if you expose yourself to steam, the steam must first condense into boiling water. Steam at 100 degrees must first change into boiling water at 100 degrees. And then the boiling water, it's hotter than your body, it's 100 degrees, will cool down to your body temperature, which is 37 degrees Celsius, right? So let's calculate the extra Q that you get out of that vapor is condensation. So what's the delta H for the condensation? It's just going to be the negative of the delta H for vaporization, right? Which is going to be equal to the negative of 40.7 kilojoules per mole. Okay, how many moles of water are we looking at? 1 mole of water. So negative 40.7 kilojoules. Okay? A mole of water is how many grams of water? One mole of water is 18 grams, right? 18.02 grams. So what is Q to go from 100 degrees Celsius to 37 degrees Celsius? Mass of water times specific heat of water times delta T. What would that be? What's the mass of the water? For 1 mole, it's 18.02 grams per mole, right? Specific heat of water, 4.18 joules per Kelvin per gram. Okay. And what's our delta T? You went from 100 to 37. That's negative 63 Kelvin. Kelvin cancels out. So that gives me how many joules per mole? 18 times 418 times 63. How much? Negative 4,045 joules. So in kilojoules, that would be negative 4.7 kilojoules. Right? I moved my decimal point 3 places. So look at this comparison. This requires 40.7 kilojoules. This releases 40.7 kilojoules. This releases 4.7 kilojoules. It's about, what's 40 compared to 4.7? 41 compared to 4.7. 40.7 divided by 4.7. That's about 8.6. The steam alone, the condensation of the steam generates 8.5 times more heat than the cooling of the boiling water to room temperature. Okay? So, steam is a much better way, for example, for if you want to sterilize something. It's better to expose it to steam than just to dip it in boiling water. The steam generates more heat. So, okay, this might be a good time to pause.